Today's lesson, we're going to be analyzing graphs, looking at the variables, telling what's going on. So take 2 to 4 minutes, complete the do now, and play the video, pause the video, and play it once you're done. So it says state the independent variable and the dependent variable. So let's start with the independent variable is always the x, whatever variable's on the x-axis, and the independent is always what's on the y-axis. So our independent variable is going to be time, and our dependent variable, which is on the y-axis, is going to be the distance driven. So we state our variables. Now we need to describe how the variables are related throughout the graph. So as time is increasing, so x is going to the right, what's happening to the y value? Well, as x increases, the y is increasing until it gets to this point right here where x is increasing and y is not increasing, where distance is staying constant, and then we rise again, so distance driven is increasing as time is increasing, and then the distance driven again is stable. We're not going anywhere as time is increasing, and that goes on for another time. So how I would describe this is as time is increasing, so as time increases, what is happening to our y-axis, or in this case the distance driven? Well, the distance driven is increasing, so the distance driven increases, but it doesn't always increase. So we're going to want to talk about those little stopping points, which if we're talking about time and distance driven, that's when the driver's stopping for a little bit. It might be to get something to eat, fill up gas. So I'm just going to say except when the driver stops for a little bit. And to be a little more specific, you can describe that is when the slope is 0. So that is at these locations right here is when the driver's stopping. So let's do now. Let's look at the next question. I want you guys to take a second to read this. I want you guys to draw a graph that would represent every single part of this drone's flight here. So read the description, pause the video, take 2 to 4 minutes, and play it once you're done. So it starts with the drone rising quickly into the air. So if it's rising, it's going to be a positive slope. And if it's quickly, it's going to be a pretty steep positive slope. So I'm going to draw a pretty steep positive slope. After that, the battery runs out and it slows down the drone. So it's going to get less steep until it reaches a complete stop. So stop at its highest point. And then it falls quickly back down until a parachute opens. And then it falls slowly back to the ground. So it should look something like that. It doesn't have to. It's not. No one's gonna exactly look like that, but it should look something like that. So let's label each of these parts. In the beginning, that's when the drone is rising quickly. And then after it rises quickly, the battery runs out, so it slows down a little bit. I'm just going to say it slows until it reaches a complete stop at the highest point. And after that, it starts to fall quickly, so it falls quickly. And right when it starts falling slowly back down, right here, that's when the parachute opens. So parachute opens here. So the drone can now fall slowly to the ground. So you could represent a drone's flight with a graph easily. Let's go to the next page. What should I be able to do? 4 things. I can interpret a graph's meaning in a real-world context. I can represent a real-world situation between 2 variables graphically. We've already done that the previous page. We're going to do a more formal question next. I can determine whether a relation is linear or nonlinear, and I can graph absolute value equations. So all of these things should be review, things we've done last year. So let's take a look at this next question here. On one spring day, Elroy noted the time of day and the temperature in degrees Fahrenheit. His findings are stated below. So here are his findings. On the set of axes below, graph Elroy's data. So let's take a look at each step. So I'm going to take a look at I'm going to try and color code the steps. At 6 a.m., so we take a look at the x-axis, it's time. Y-axis is temperature. Take a note of the y-axis. It's going up 2 degrees every single box. You can fill it in if you want to. You don't have to. So at 6 a.m., the temperature was 50 degrees Fahrenheit. So I'll plot 6 a.m., 50 degrees Fahrenheit. For the next 4 hours, so from 6 a.m. to 10 a.m., the temperature rose 3 degrees per hour. 3 degrees per hour. So 3 is not up 3 boxes, but each box counts as 2, so it'll be up a box and a half. So that'll be 7, 8, 9, and 10. Draw that line. So that's the first part. Let's take a look at the second part. Then for the next 6 hours, so it'll take us from 10 a.m. all the way to 4 p.m., the temperature rose 2 degrees per hour. So that's going to go up 1 box each time. So that'll be 11, 12, 1, 2, 3, 4. Draw your line, connecting with the other one. Then the temperature stayed steady, so the temperature is not going up or down until 6 p.m. So until 6 p.m., we just have a steady line. It's not going up, it's not going down. For the next 2 hours, we're dropping 1 degree per hour. So make sure you don't go 1 box, because 1 box is 2 degrees. So for the next 2 hours, we go half a box, then half a box. So we'll go from here to there. And the last part, the temperature then dropped steadily until the temperature was 56 degrees at midnight. So I'm gonna go to 56. I'm gonna go to 12 degrees, 12 midnight, and I'm gonna plot 12:56, which would be right here. And then I'm just gonna connect the line up here. So that's what your graph should look like. So let's now state the entire time interval, so not just part of it, for which the temperature was increasing. It starts increasing, so we start at 6 a.m. So from 6 a.m. it's increasing all the way till right here, which is 4 p.m. So from 6 a.m. to 4 p.m. That is when it's increasing. The temperature is increasing because it has a positive slope. Next, determine the rate of change in degrees per hour from 6 p.m. to 12 midnight. So let's first take a look at the points for 6 p.m. and 12 midnight. 6 p.m. is right here. And 12 midnight is right here. I'm just going to think of it as change in y over change of x. There's so many ways of doing this. You could write down the points, which I was thinking about doing, but I'm just going to look at it as change in y over change of x. M equals, let me get a different color. M equals change in y over change of x. So the change in y, I'm going from 74, so I go down 2, 4, 6, 8, 10, 12, 14, 16, 18. So I'm going down 18. So I'll be negative 18 over. So I'm going to the right. 1, 2, 3, 4, 5, 6. But remember, each box counts as 2. Actually, not for the x, each box counts as 1. Sorry. So that'll be negative 18 over 6. I got confused with the y there. Negative 18 over 6 is just negative 3. And make sure you don't want to have those lines. If you did it the way I did it, oops. If you did it the way I did it, make sure you don't have those lines on your graph. You want to erase that slope work. So that'll be negative 3 degrees Fahrenheit per hour. Make sure you put the units on that. It's degrees Fahrenheit goes on top because that is the y. And why is it per hour? Well, the hour goes on the denominator because time is the x-axis. And that's it for this one. Let's go to the next page. We're moving on to linear versus nonlinear relations. I want you guys to take a minute or two. Do the do now. Pause the video and play it once you're done. What makes a relationship between two variables linear? So the main thing is here, it has a... What's the key words? A constant rate of change. So it has a constant rate of change are the keywords. Keywords constant means it's not changing. So between any 2 points you pick, it doesn't matter if you choose these 2 points or you choose these 2 points. So between any 2 points on the line, it will have a constant rate of change. So the slope of the rate of change is always going to be the same. But if it's nonlinear, it's not going to have a constant rate of change. So it does not have a constant rate of change. And that's what we're going to use to apply to any question that asks us if it is linear or nonlinear. So looking at the next example, Rachel and Mark were given this information, and Rachel wants to model this information with a linear function. Mark, on the other hand, wants to use an exponential function, think nonlinear. So which model is the better choice? And we will be doing exponential equations and functions later on in the year. It's like one of our last units. But so think about nonlinear right now, linear and nonlinear. Which model is a better choice? So let's take a look. Let's think of it as change in y over change of x. So let's go from point to point. From the first 2 points, we have a change in x of plus 1 and a change in y in plus 60. So our slope there would be 60 over 1, which is 60. Okay. Between every single point, if this is linear, we should have a rate of change of 60. So let's go to the next two. We go from 2 to 3, which is plus 1. And from 280 to 350, which is plus 70. Oh boy, that's 70 over 1, which is 70. These do not have a constant rate of change. They do not have the same slope or rate of change. So therefore, we do not want to choose a linear function. We want to choose the nonlinear, the exponential function. So which model is a better choice? The exponential function. And make sure you explain your reasoning here. So it's explain why you chose that method. And whenever it says explain why, if it's linear or nonlinear, or linear and anything else, just say it has a constant rate of change if it's linear, but in this case it's not linear, so because the exponential function, because it does not have a constant rate of change. So let's take a look at the next question. And before we take a look at the next question, always, I can't stress it enough. If it asks you if it's linear or exponential or linear or nonlinear, just say if it's linear, constant rate of change. For exponential or nonlinear, not a constant rate of change. That will always be a great explanation for that. So which function below represents a linear function? So let's think of a linear function. We have 4 different types of equations here. When we think of linear functions, we think of y equals mx plus b is the most common one, the slope-intercept form. Which one here is in slope-intercept form? Well, look at D. We have y equals m, which is negative 2 over 3, x plus b, which in this case is negative 1/2. So which represents a linear function? Well, the one in y equals mx plus b form, which is choice D. Let's go to the next page. Which situation can be modeled by a linear equation? So if it can be modeled by a linear equation, what can be said about the scenario? Well, what defines a linear function? It has a constant. A constant what? Rate of change. So we want to figure out which scenario here, 1, 2, 3, or 4, has a constant rate of change. So what I'm going to do for that is I'm just going to try and make a table for each of them and see which one has a constant rate of change. I think that's the easiest way of going about it. So let's take a look at number 1. We have the population of bacteria triples every single day. So we have the population and we have the days. So day 1, day 2, day 3, day 4. I'm just starting from day 1 and going on. You can keep going on if you want to. After day 4. Population, just put a random population. Let's try 2. So if it starts with 2 bacteria, that means it triples on the second day to be 6. That triples again to 18 times 3. And triple that again, multiply that by 3 again, and you'll get 54. Here you'll see the x is going up by 1 each time, so that's good. What's the y going up by each time? That's going up by plus 4, then it's going up by plus 12. So automatically the slope goes from 4 over 1 to 12 over 1, so it can't be choice 2. Let's check out choice 1. Let's check out choice 2. So choice 2 says the value of a cell phone depreciates at a rate of 3.5% each year. Whenever we're talking percent, that is never linear. Think about this in a different way. So if I ask you for 3.5% of 100, multiply 100 by 0.035, and you'll get 3.5. But then think about 3.5% of 1, it's going to be much less than 3.5. So when you take percentages of numbers, it's always different depending on the number. So I can do a quick little XY table for you guys for this one if you want to do that also. So the top would be the value of the cell phone, so value of cell phone. And the years would be the independent variable. So let's just do year 1, 2, and 3. And let's say the first year, say it starts out at $100. So that means if it depreciates, it's going down 3.5%. So do 100 times 0.035. It goes down 3.5, so $3.50. Which means we go from 100 to $96.50. Okay, so that's going down minus 3.5 as x is going up once. And then as x goes up once again, what's happening to the value? So when we go 1 year ahead, what's happening to the value? We'll do 96.5 times 3.5. Oh, sorry, not 3.5. Excuse me. 0.035 because it's a percent. Very common mistake there. I'm glad I caught it. It's a percent, so we have to multiply, take out a percentage, so you move it to, moving it back twice, so it'll be 0.035 is what we're multiplying by. So do 96.5 times 0.035, and you'll get 3.3775. It depreciates, so you're going to subtract 96.5 from that to see what our price is going to be. And that'll be 93.1225, which would be 93.12. So you're subtracting 96.5 minus 3.3775. So that now goes to $93.12. And you'll see that difference is not the same. 96.5 minus 93.12. We're going down 3.38. Not a constant rate of change. So it's a lot of work for a percentage problem to see that. But if you just see percentage, just know never going to be linear because percentage changes depending on the number. Let's look at number 3. An amusement park allows 50 people to enter every 30 minutes. You can take a look at it and be like, oh, that means every 30 minutes, 50 people are being let in. So people, and then minutes. So every 30, it allows 50 people in. So in the first 30 minutes, we have 50, then 100, then 150. You would see it's going up 50 each time for the people, and the minutes is going up 30 each time. So we are going to have a constant rate of change here, so it would be choice 3. Real quick, just to check choice 4 to make sure that one's incorrect. A baseball team eliminates half the teams each round. So if we did round here and teams here, as the rounds go up, think about the NCAA tournament. The basketball tournament starts with 64, then the halves again. So although it's dividing by 2, the differences are subtracting from 32, then you're subtracting 16, then you're subtracting 8 teams, while the x's only go up by 1 each time, so the rate of change is not constant there. So that's for that question. Very similar question. It says on the next question is, what characteristic of all linear functions is that they change by what? So they're always going to change by an equal number since it's a constant rate of change. So I'm going to cancel out everything that says unequal. And let's talk about what equal differences over equal intervals means compared to equal factors over equal intervals. So I'm going to do one of each. I'm not going to tell you which one's which. So here's I'll put the x on top. It doesn't really matter which one you put for the table. Just make sure you know when you check the slope, the y always goes. It's change of y over change of x. So let's do, we'll have this, the top one be x be 1, 2, 3, 4. And then the y would be 2, 4, 8, 16. And then 1, 2, 3, 4 again for the bottom relation. And we'll have 5, 7, 9, 11. One of these is linear and one of these is not. I want you guys to take a minute, think of which one's linear, which one's nonlinear, and then match choice 1 or choice 3 with one of these examples here. Pause the video once you're done. So let's take a look at the difference between equal differences and equal factors. If you take a look at the top one, we're multiplying by 2, multiplying by 2, multiplying by 2 each time. But on the bottom example, we're adding 2, adding 2, adding 2. So the bottom one is equal differences. The top one, we're multiplying, it's equal factors. And which one's linear? Well, linear, we don't look at the y being multiplied. We look at the difference. It's a change in x over change of y. So it'd be plus 2, plus 4, plus 8 for that top relation, which is not a linear function. It does not have a constant rate of change, where the bottom one does. The rate of change is always 2 over 1. So it would be equal differences over equal intervals. Let's go to the next page. On the next page, we're going to be talking about graphing absolute value functions. For the do now, what I want you guys to do is graph that function without a calculator. Pause the video, try and graph that without a calculator, and play it once you're done. So what I'm going to do for this is the best way of graphing when it's not y equals mx plus b form, which is clearly is not, it's y equals the absolute value of x, is to do an xy chart. So we have x, we have the equation, we have y, and then I like to include a fourth column for xy, so there's no confusion on the point that we're actually graphing. So let's take a look at this. I'm not going to write negative 20 for x right off the bat, because negative 20 is not going to be plottable. We want values of x that we can plot, that we think we can plot. And if you plug in like 15 in for x and you figure out, oh, I can't plot that in my graph, just use a smaller value of x or a larger one depending on your value. So I'm going to choose to do negative 2, negative 1, 0, 1, and 2. So I'm going to plug in that value, negative 2, and for x here, the absolute value of negative 2 is 2. So my point that I'm plotting is negative 2, comma 2, which would be here. Do the same thing for negative 1. Absolute value of negative 1 is 1. So my point would be the x, comma the y. And I'm going to do this for every single point that I have. And lastly, absolute value of 2 is 2. So my point would be 2, comma 2. So we see the pattern. We can just draw our straight line from here all the way up, connecting all the dots, and straight line from here all the way up, connecting the dots. Make sure you label. And that's how you graph y equals absolute value of x. Just plug in points for x, figure out their y, and plot those points. Absolute value equations have the V shape. So if you don't have a V shape, I see this a lot. Students choose like these 3 points right here. I'll do them in blue. And then they connect them and they forget to do ones on the other side of the vertex. And they just go, boom, that's the line. Make sure you plot more points. You'll see that it's going to bounce back up at some point. I also want to show you guys how to graph this in your calculator. So I'm going to erase this, and we're going to use the calculator for this. We need a calculator. I don't know where calculator is. 1 second. Expelliarmus. There's the calculator. Okay. Whew. Let's clear out anything that's in our calculator. Okay. And now we're going to graph our equation. So if you remember where absolute value is, you press math, you go over to num, which stands for number, and abs is absolute value. So press enter on that. We want the absolute value of x. Press graph. Should look something like that. We just graphed it. It did. So what would I want to do here? Let's check out our table. And now we're at the negative 30s. Let's scroll till we can see a point. This is very much like I was talking about before. We want points we can graph. So let's go to some points we can graph. Make sure you get that vertex. The vertex is where it turns. So if you look here, we go from negative 6x. Negative 6 is the x and 6 is the y. And we're going down in the y from 1 all the way to 0. And then it goes back up. So we want to make sure we plot that 0, 0 on our graph. So when we do our xy table, x, y, we want to make sure we have that 0, 0 vertex in the middle so we can see the bouncing. And then we can look at negative 1, comma 2, negative 2, comma 2, and we can just copy down points as such from our table, plot them, and do the same thing. I would recommend plotting all the way up. Follow that pattern so you don't make any tiny little minute mistake. graphing. And then graph a straight line, connecting all these points, and then connecting all these points. Make sure you put arrows on the end, lines going all the way through the graph, and that'd be y equals absolute value of x. Make sure you label it. On the next page, I want you guys to take a couple minutes, graph this equation as you see fit. You can do it without a calculator, with a calculator. Just if you do it without a calculator or with, make sure you have the vertex in your XY table. Pause the video and play it once you're done. I'm going to choose to use the calculator. So I'm going to go to y equals. I'm going to plot the absolute value math over abs x minus 3. Get out. Make sure you get out of the absolute value here. So you press over. Plus 2. My graph should look something like that when I graph it, so I know in case I make a mistake graphing, I can look back at my calculator and be like, okay, if it doesn't look like that, I did something wrong. Let's check out the table. Where is the turning point? It's going down from 11, 10, 9, 8. It's going down. Oop, look at 3, 2. 3, 2. That's where it starts going back up after that. So I'm going to scroll down here. And I'm just going to copy down an XY table. So just off the side, this will count as your work. You have X and Y. So our vertex or turning point is 3, 2. So I'm going to put that in the middle of my graph. I'm going to do 3 to the left and 3 to the right of that. So it'll be 2, 1, 0. Then 4, 5, 6. And just copy down the points from there. So it'll be 3, 3, 4, 4, 5, 5. Make sure you plot all those points. Draw your line. I would use a ruler if you have one. Arrows on the end. And then make sure you label it. That'll be f of x is equal to the absolute value of x minus 3 plus 2. And it should look like that. So that is it for today. Make sure you do the success criteria and the classwork.